We'd like to welcome you to our Math 102 Flipped Classroom Video Lecture Series. The first lesson, which is on Unit 1, Topic 1, you'll be doing prior to the beginning of class, and we will ask you to keep your notes on loose leaf of some type. You will bring these notes into class, and we'll have our first quiz. And we'll give you more detail on that as we go on. Now, in Unit 1, we cover these 4 sections. And you don't have to take any notes on anything so far. This is just background. Now, once you get to class, and this will be whenever we meet first, I will physically give you a lecture booklet. And in future lessons, in this booklet, you will keep your flipped classroom lecture notes. And each day, as we mentioned, you will have a quiz using these notes. They are open notes quiz. As we do them and ask questions on our quiz, they will follow chronologically the way we gave the lesson. So what is done in the beginning of our notes will be the first questions, and then in the middle, those questions, and then at the end, we often use examples that are in the booklet, as you will see. Now, this notebook is checked periodically and makes up 5% of your end-of-term grade. The quizzes themselves make up 10% of your end-of-term grade. So, starting now on your loose leaf, Section 1.1, Real Numbers, Order, and Absolute Value. Now, I'd like to show you what your notebooks would look like, and we'll go through a few pages of it, even though you won't have it for the first lesson. Generally, on the left side of the notebook is a blank page, and that's where normally you would put the notes. And over on the right, and we're in section 1.2, there are examples, as you'll see toward the end of the lesson, where we do want you to put answers in there. And if you need to show work, there's usually area to the right here that is free. Showing you another page of this. There's the second page here. There we go. No. There we go. Well, we're all in section 3. So again, you take your notes usually on the left, being clear and neat and orderly, and then working out examples that are associated to your text on the right side. And notice I included lots of work of how I got answers. Now again, all of this is going to be very useful on your open notes quizzes, and you are allowed to use your notes on your test. So, the first thing we're going to do is look at sets of real numbers. And this is what we'd like you to write in your notes. So, what is a set? Well, it's just a collection of things, and in math, of course, it's going to be a collection of numbers. And we're going to use this topic in a number of our units. So, a good idea to get some good notes. The first set of what we're calling real numbers are natural numbers. So you're going to write this in your notes, natural numbers, and then you're going to put a brace and we're going to start listing them. 1, 2, 3, 4. Now this continues on and on and on, and we indicate that it continues in this pattern by putting 3 dots, which we call an ellipsis. And I would include that word in my notes, and its definition is that this is a symbol used to show a pattern that continues. And you might say, where does it continue to? Well, out here is infinity, which is a concept indicating it never ends. Now, I have listed this set of real numbers using a special notation. This is called roster notation. Or a common way is listing notation. Roster is the more formal word for how we are showing this. Now, what I've drawn here, and I'd like you to draw in your notes, later it'd be in your booklet, but is what is called a number line. Now, on a number line, we put a 0, then 1, 2, 3, 4, 5, 6. And if I were to graph the set of natural numbers on a number line, again, I could put the numbers there. I would do so by putting a little dot at the numbers I'm interested in. Now, to indicate that this pattern continues, that is, the ellipses, I just make my arrow a little thicker here. So this pattern goes on. And this is the graph of natural numbers. So you have a number of items so far in your notes. Now, the next set of numbers, referred to as whole numbers. You want to write that down. Now, how do natural numbers differ from whole numbers? And the answer is we add a 0. So just by adding a 0 and graphing it here, we now have made the graph of the set of whole numbers. Everything else is the same, except now we have added one element, that is a 0. All right, let's go on. Now, as we continue on the number line, and let's just sketch on this official one here, we have a 0, a 1, a 2, a 3, a 4, and we've indicated our ellipsis by thickening that arrow. Are there other numbers on the number line? And the answer is yes. And that'll make up our next set of numbers. So on the other side of 0 to the left, we have the negative numbers. These are all positive numbers. So if we take 1 and its opposite, when we add a number and its opposite, we get a 0. 2 and its opposite, we get a negative 2. That would add up to a 0, and so on and so forth. And then we go to negative infinity on this side, and positive infinity on this side. We have what are called signed numbers. And this set of numbers now, and we'll just sketch it for you here, it would be dot, 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 coming from negative infinity. You can start here, -2, -1, 0, 1, 2, continuing this pattern. We get this set of numbers that are called integers. And this should be included in your notes. And we see that in our next slide here. Now, we're going to go back to the number line to introduce our next group of numbers. And we see the number 1/2. Well, where is 1/2? Well, it's right there, approximately. I might be a little off. Now, 1/2 is not an integer. But what is it? Well, we call a subdivision of numbers between integers fractions. So we can show the fraction 1/2 on the number line, and then a -1 2/3 would be about there, a -1 2/3. So those are numbers that are on the number line, but how do we describe them? Well, any number, as they say, and this particular way of showing it, let me go over that and say this is called set builder notation. Write this in your notes. Where we have a brace, and we read it, x is such, this vertical line is such, that x is a quotient, that is a fraction, of two integers with the denominator not equal to 0. This is a set of what we call rational numbers. Now, can we indicate 1 in a form of a fraction, in a sense? And the answer is yes. This would be like 1/1. We don't usually write the 1 when it's a 1, when it's a whole number. And this is going to be 2/1. So this is -1/1. So all whole numbers could be written over 1. So all whole numbers are rational numbers, and as is the natural or counting numbers that we mentioned earlier. So we're building up our definitions of sets of real numbers. Now, something else I'd like to include here is that if we take the fraction 1/2 and change it to its decimal form, it becomes 0.5, and then it just stops. We say it terminates. And if we take another fraction, which is about like here, which is 1/3, approximately, and convert that to its decimal form, it's 0.3333, keeps repeating, and we can just put a bar, a repeating bar, over the part that repeats. It doesn't terminate, but just repeats a pattern. We also say fractions in helping to define rational numbers. In their fractional decimal form, terminate or repeat or show those patterns. These are considered rational numbers, because we're getting ready to introduce our next type of real number. Now, going back to our number line and our next set of numbers, there is 0, there's 1, there's 2, there's 3. Now, we talked about fractions, 1/2, 1/3, and we also had negative ones on this side. 1 and 1/2 would be right there. But right a little less than 1 and 1/2, right there, is on the number line the number, the square root of 2, which in its decimal form is 1.414. And in my calculator, as I went on, it only goes up this far in the display window. But notice there is no pattern. It doesn't terminate, and it doesn't have a repeating pattern. Numbers, like the square root of 2, the square root of 3, and that would be about there. And eventually you get to the number 2, but 2 in its radical form would be the square root of 4, which is a perfect square. So when you take the square root of 4, you get a 2, even though it's shown under the radical sign. That if you don't have a perfect square under the radical sign, then these numbers are considered irrational numbers. And they're on the number line, but because they don't terminate in their decimal form or have a repeating pattern in their decimal form, they are considered, once again, irrational numbers. Now, are there other irrational numbers? Yes, some of the famous ones would be pi at this stage. And then a little later in our lessons, we're going to have the letter E, which is a famous rational number you may or may not know. But that's about here. And that's about 2.7, and that's irrational. It goes on and on. Okay. Now, remember, the decimal form 2.7 terminates, so that's not the real value of E, but it's close to it. All right, let's go on. Now, this is a picture that I actually have in your booklet once you get them, but if you wanted to sketch this in your notes, that would be fine. So what are the real numbers? Well, the real numbers are all of the numbers on the number line. And they include natural numbers, which are sometimes called counting numbers. Adding a 0, you get whole numbers. Adding their opposites on the other side, you get the integers. Then between the integers, you get fractions. But remember, natural numbers are all of these things. Whole numbers are all of these things, except they're not natural numbers. And then we've introduced the irrational numbers. So now, this is something we want you to note carefully in your lecture notes. We're giving you example 1, and the PP refers to PowerPoint. So write that, example 1, PP. They're asking you to identify from this series of numbers in roster notation which are the natural numbers, which are the rational numbers, and which are the real numbers. So, again, you're going to write this out. And let's look for natural numbers first. No, no, no. This is no and no. Remember, this is not a perfect square. If we had a 2, I should say the square root of 4 here, that would be a natural number because that would simplify to 2. But when it's not a perfect square, it's irrational. So how about the rational numbers? Well, this is rational. This is rational. This is rational. This is rational. And the one that's not rational is the radical, the square root of 7. Because in its fractional, decimal fractional form, it would not repeat or terminate. And for real numbers, all of these are real numbers. They're all on the number line. And there's our solution. Now, you may have picked up that one of the nice things about having your own personal video is that you can pause this. You can take the notes and keep in mind that these can be done at a faster pace. You could speed it up a little bit. Down at the bottom, there is a little key to let these go faster. All right, order in the real numbers. We can compare real numbers or their ordered form by using ideas of equality and inequality. So this is something you want to include in your notes. This is the law of the trichotomy, which states that for any two numbers, A and B, one and only one of the following is true. That A could equal B, or A could be less than B, and A could be greater than B. But only one of these things can be true at a time. This basic law of mathematics is called the law of the trichotomy. You should have that written up in your notes. Now, we also have inequality symbols, and these should be written up and defined. This one means less than or equal to, as is described there. Now, notice there's a less than and an equal as part of this. So let's look at an example here, but this is background information. 5 is less than or equal to 7. And you might say, well, it doesn't equal 7, but is in this form part of it true? And the answer is yes. So if part of it is true, then it is true. The symbol is greater than or equals to, again, is made up of an equal sign and greater than. All right, going on to another key word for your vocabulary, the additive inverse. And we did this a little bit when we defined the set of integers, that you have a number on the right that has a number on the other side of the 0 as its opposite. Well, that is its additive inverse. What you would add to it to have it equal 0. So for instance, 3 and a negative 3. These are additive inverses and again referred to as opposites of each other. So pause, take some notes. This could be a quiz question. Now, we also have another rule in mathematics called the double negative rule. That for any real number x, here we're saying x is negative x. This negative sign in front is often read as the opposite. Rather than just saying it's negative, we say it's the opposite of a negative x would be a positive x. Again, as part of our definition of integers, the opposite of a number is what would make it 0. So the opposite of a negative makes it a positive. This is the double negative rule. You may have heard the expression, two negatives make a positive. And that's what this is. Now, another item we need for our vocabulary is absolute value. Now, the symbol for absolute is two vertical lines, in a sense making boundaries of what is inside. So this symbol is read as the absolute value of x. Now, the absolute value of anything is never negative. And what it is it's in a sense, kind of a counting or a distance. A number is from where it is to 0. And distance is measured in positive values. So here's the rule. X, the absolute value of x, is always going to be equal or greater than 0. And in its negative form, it would have to be positive. And we'll show you some examples. And in your notes, you want to put example 2pp. This is from our PowerPoint slides, so that when I'm referring to them in our Open Notes quiz, I will often say example 2pp, and then let's say letter A or B or C or D. So here A, the absolute value of 4 is 4. The absolute value of negative 2, again, will always be its positive value, a 2. And these are written up down below. Now, for number, or letter C here, this is a little tricky, so be careful of this. The absolute value of a negative 3 is a 3. But now we have to deal with that negative in front that we apply. So again, even though we're asking for absolute value, we have to treat the sign that's in front. Now over here, these were positive. You can think of this as somewhat being like a negative 1 times the absolute value of a negative 3. So the absolute value of 3 is, negative 3 is 3, and then you're timesing it by a negative 1, so this gives you a negative 3. Students have a problem with this from time to time. Now, absolute value is also treated as a grouping symbol. So here we have a 1 minus 8. This will give us a negative 7. And then we take the absolute value of negative 7 and get 7. And there are solutions here. So again, in your notes, you're going to write example 3. PP indicating it's from our PowerPoint slides. Here we have a given temperature reading of the days below. Which day had the greatest amount of change? So we had AM temperatures were this, that's morning. Afternoon temperatures were this. And we're looking at the amount of change. Well, here there was 19 degrees positive, 23 degrees positive, but this day had a negative 27 amount of change. So which is the largest? And here we're looking, in a sense, at their absolute value. How much change was there? So the greatest was the negative 27, even though it's given as a negative. And we think of it in this term. Now, for something like this, you don't have to write the chart down. You just want to write the answer and maybe a little bit of what was going on. So here's the solution maybe. Day 3 had the greatest change at the absolute value of negative 27, which was then 27 degrees. Okay, now we're changing mode, and since you're doing this in your notes, you will have to write out some of these, but normally they are in your booklet, so you wouldn't have to. But on our first day, these you'll have to include in your notes. And for these, you're just going to write example 1. No PP, because these are from our textbook. So, let's do these together, and as we go along. For question 1 now, what are the natural numbers? Well, as we look at our list, the only natural number is 5. So natural number, you're going to put here a 5. Whole numbers, well, it would be the 0 and the 5. Integers, well, this is an integer. And let's write that, negative 5, 0, and 5. Now remember, integers include all of these others. Now, rational numbers. Well, it would be all that we have listed so far. 2/3, a negative 2/3 has a repeating decimal, so that's rational. Square root of 2, we said, was irrational, and this is also rational, because that would have a terminating decimal. So all of these then written for rational numbers. Put them in your notes. Now for the irrational number, the only one here, and I'll change colors for that, is this one, the square root of 2. And for real numbers, it's all of these are on the number line. And again, you can pause. And there you see them as well. Now, generally, for these examples that we're doing from the textbook, I will initially have the example and then followed by the solution. Again, you can pause, and if you have any questions on the earlier material or any of these examples, that's what you are to bring to class. We help that in class. And I should clear that up. Okay, now what we're asked to do is to determine if these statements are true or false. So again, you'll write these down. Normally they'd be in your booklet, but you're going to write them down today. 6 does not equal 6. Well, that's false. 5 is less than 19. That's true. 15 is less than or equal to 20. Now we said in this configuration, only part of it needs to be true. 15 is less than 20, so that's true. 25 is greater or equal to 30. Now, neither part of that is true, so this is false. 12 is greater or equal to 12. In this configuration, only part needs to be true, and it is equal, so therefore it's true. Okay. And there is the solution. Pause if needed. Alright, here we're asked to simplify. It's going to take time to write them down, but have them in your notes. And I'll change back to my nice red. I like the red. Absolute value of 5 is 5. Absolute value of negative 5 is 5. Now the absolute value of 5 is 5, but we have to multiply by negative 1 here. So this becomes negative 5. Now absolute value of negative 14 is 14, but we multiplied by negative 1, so it becomes negative 14. Here we're using grouping symbols as absolute signs. This becomes a positive 6. Absolute value of positive 6 is 6. Now here this is still 6, but now we have to multiply it by that negative 1. Negative 6. And again, of course, you can pause these. Try these on your own. Now, here, again, you don't have to copy the chart down, but let's just look at it here. Because we're looking to see the greatest change and the least change. So as we look at this, which is going to be the least? Well, here we're looking for absolute values. So the least would be 3.6. And the greatest, even though it's negative, the greatest amount of change, its absolute value, would be 12.2. And if you agree to that, then you're hopefully, that's good. And then there is the solution of all of this, and I will drop that down here a little bit so you can see it a little better. Okay. And that completes our first lesson. Now, these are exercises that'll be in your textbook. This used to be associated with a different chapter. Every once in a while you may note that, but in our lessons here we have them lined up to match what your current textbook is. And good luck on your open notes quiz. If you have some good notes, you should do very well.